Hello everyone, my name is Madhuri Gupta, Assistant Professor, Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today we have the summary wrap up class. So, we have each week details based on course outline. So, in week 1, Introduction to AI and Problem Solving. In week 1, we kicked off our journey into artificial intelligence AI by defining what AI is and why it is important. We explored the problem solving which is at the core of AI. AI systems are designed to solve complex problems. We delve into state space search, a key technique used in AI, and discuss two classical problems to illustrate this concept, the 8 puzzle problem and the water jug problem. In the first week of our course, we set the foundation by introducing artificial intelligence and exploring the fundamental concept of problem solving, which forms the backbone of AI. This week's topic include an overview of AI, problem solving techniques and practical problem solving examples. Introduction to artificial intelligence. AI is multidisciplinary field of computer science that focuses on creating intelligence machine capable of performing tasks that typically require human intelligence. We discussed the significance of AI in various domains including healthcare, finance, autonomous vehicles and more. AI encompasses a wide range of technologies such as machine learning, natural language processing and computer vision. Problem solving. Problem solving is at the heart of AI. AI systems are designed to solve complex problems and make decisions based on data and logic. We emphasize that problem solving involves defining a problem, searching for possible solutions and selecting the best solution among alternatives. Problem solving in AI can be approachable systematically using various techniques and algorithms. State space search. To solve problems systematically, we introduce the concept of state space search. It involves exploring a space of possible states or configuration to find a solution. State space can be visualized as a graph where nodes represent states and edges represent transitions between states. We explain how state space search is used to model and solve a wide range of problems. Problem examples: 8 puzzle and water jug problem. To illustrate state space search, we presented two classical problems. 8 puzzle problem. This is sliding puzzles with 8 numbered tiles that must be arranged in a specific order. It is an example of search problem where each move represents a state transitions. Water jug problem. In this problem, you have two jugs of different capabilities and need to measure a specific quantities of water. It demonstrates the applications of state space search to real world scenario. Key takeaways. Week 1 laid the foundation for the course by introducing AI as multidisciplinary field with vast applications. Problem solving is a central theme in AI and state space search is a fundamental technique for systematically finding solutions. Real world problem such as the 8 puzzle and water jug problem can be represented and solved using AI techniques. As we progress through the course, we will build upon this foundation concept, exploring various problem solving algorithms, search strategies, knowledge, representation methods and AI application in depth. In week 2, we have explained about search algorithm. In week 2, we continued our exploration of problem solving by taking more problems like the missionaries and cannibal problems. We introduced the concept of search algorithm which help AI systems navigate complex spaces of possible solutions. We explored blind search methods including depth first search and breadth first search, and discussed their advantages and limitation. We also ventured into informed search while involves using heuristic functions to guide the search process, and discussed hill climbing search as an example. Search algorithm plays a fundamental role in the field of artificial intelligence and are essential for solving complex problems. These algorithms help AI systems through the large solutions spaces to find optimal or near optimal solutions. In this discussion, we will explore search algorithm in AI, their types and their applications. Types of search algorithms. Blind search algorithms. These algorithms do not have information about the goal state and explore the search space systematically. Two common examples are depth first search and breadth first search. Depth first search. Depth first search explores as far as possible along each branch before backtracking. It is often implemented using a stacked data structure, making it memory efficient, but may not find the shortest path. Breadth first search. Breadth first search explores all the neighbor nodes at the current depth before moving to the next level. It guarantees finding the shortest path, but may require more memory. Informed search algorithms. In contrast to blind search, informed search algorithms use heuristic information to guide the search towards the goal state efficiently. Example include best first search, A star search and AO star search. Best first search. This algorithm selects the most promising node based on a heuristic function. It is not guaranteed to find the optimal solution, but often performs well. A star search. A star combines the advantages of both best first search and depth first search by using a cost function and a heuristic function. It is considered one of the most efficient and widely used search algorithms. AO star search. AO star extends A star by considering multiple paths simultaneously and selecting the most promising one based on a dynamic evolution function. It is suitable for problems with uncertainties. Applications of search algorithms in AI. Route planning. Search algorithms are commonly used in route planning applications such as GPS navigation systems. They find the shortest or fastest path between two locations on a map. Next is puzzle solving. Search algorithms are applied to solve puzzles like 8 puzzles, Rubik's cube and Sudoku by exploring possible states. Game playing. In game AI, search algorithms like min-max and alpha-beta pruning are used to make optimal decisions in games like chess and tic-tac-toe. Natural language processing. Search algorithms are used for language parsing, machine translation and information retrieval in NLP applications. Planning and robotics. AI systems in robotics use search algorithm to plan optimal paths for robots in dynamic environments. Constant satisfaction problem, CSPs. Search algorithms help find solution to problems where variable must satisfy certain constants. Next is challenges and consideration. Complexity. The efficiency of search algorithm can vary significantly based on the problem's complexity and chosen algorithms. Some problem may have an enormous search space. Heuristic informed search algorithm heavily depend on the quantity of heuristics. Poor heuristic can lead to suboptimal solutions. Memory uses. Some algorithm like BFS can consume a lot of memory, which may be concerned in resource constrained environments. Optimality versus efficiency. There is often a trade-off between finding an optimal solution and the time and resource required. A star is known for balancing this trade-off effectively. In conclusion, search algorithms are vital component of AI, enabling machines to explore and navigate complex solution space efficiently depending on the problem's characteristics. Different search algorithm may be more suitable, and choosing the right one is a critical decision in AI system design. Now, week 3. Week 3, informed search. Informed search, also known as heuristic search, is a category of search algorithm used in artificial intelligence and computer science, unlike blind search, which explore a search space without any knowledge of the problem. Informed search algorithm utilize heuristic information to guide the search process more efficiently. This heuristic information helps in making informed decision about which path or nodes to explore, ultimately leading to quicker problem solving. Here is a more detailed discussion about informed search. Key concept in informed search. First, heuristic function. In informed search, a heuristic function is crucial component. It is an estimation of how close a given state is to the goal state. The heuristic function assigns a cost or value to each state, helping the search algorithm prioritize states that appear promising. A goal heuristic function should be admissible, never overestimate the true cost, and consistent. Second, greedy best first search. Greedy best first search is a simple informed search algorithm that select the most promising node based on the heuristic function. It tends to focus on paths that appear to be closer to the goal without considering the entire path cost. While efficient, it may not always find the optimal solution. Next, A star search. A star is one of the most widely used and versatile informed search algorithm. It combines the advantages of both breadth first search and greedy search. A star evaluates nodes based on a combination of the cost to reach a node and the heuristic estimate of the cost to reach the goal from that node. The algorithm expands nodes in increasing order of the sum of these two values. Admissibility and optimality. A star is admissible, meaning it will always find an optimal solution if one exists, as long as the heuristic function is admissible. In other words, A star will never overestimate the cost to reach the goal. This property makes A star highly desirable for a wide range of problems. Next is memory and time complexity. While A star is highly effective in finding optimal solutions, it can be memory intensive as it needs to store all the general nodes. Various enhancements such as iterative depending A star can be used to manage memory consumption while relating optimality. Applications of informed search. First, route planning. Informed search algorithms like A star are commonly used in route planning applications such as GPS navigation system to find the shortest or fastest path between two locations. Next, puzzle solving. Heuristic search is frequently employed in solving puzzles like the 8 puzzles, where it can efficiently explore all puzzles state space to find a solution. Next is game playing. Informed search algorithm like A star can be used to make optimal decisions in board games like chess and checkers, where finding the best move is essential. Next is robotics. Robots often use informed search for path planning and navigation in dynamic environments. Next is natural language processing, NLP. In NLP applications, informed search can be used for parsing, machine translation and information retrieval tasks. Now, challenges and consideration. Heuristic quality. The effectiveness of informed search heavily relies on the quality of heuristic function. An inaccurate or purely designed heuristic can lead to suboptimal solutions. Memory and time trade-offs. Some informed search algorithms may consume significant memory, making them less suitable for resource constrained environments. Balancing memory and time consideration is crucial. Informed search algorithm, particularly A star, are essential tools in AI and are widely applicable to various domains. When designing AI system, it is important to carefully select or design heuristic function to ensure efficient and effective informed search. Week 3 has dedicated to informed search algorithm, which are more efficient in finding solutions compared to blind search. We covered best first search, A star search and AO star search, which are widely used informed search techniques. These algorithms make use of heuristic to make intelligent decisions about which path to explore, leading to quicker problem solving. Now, week 4, constant satisfaction and game playing. Certainly, let us discuss constant satisfaction problem and game playing in context of artificial intelligence. Constant satisfaction problem are a class of computational problems where the goal is to find a solution that satisfy a set of constants. Here are the key concept: variables. In CSPs, there are variables that need to be assigned values from a domain to specify constants. Variables can represent various entities or aspects of the problems. Next is domain. Each variable has a domain, which is a set of possible values it can take. These values must be chosen from a predefined set. Next is constant. Constants are logical restrictions that dictate how variable must be assigned values. Constants define the relationship between variables and limits the possible constants of values. Examples of CSPs. First, Sudoku. In Sudoku, each cell must be find with a number from 1 to 9, subject to constant that no number can repeat in a row, column or 3 by 3 subgrid. Next is n-queen problem. In the n-queen problems, you must place n queens on an n into n chessboard in such a way that no queens threaten each other. That means, no two queens are in same row, column or diagonal. Next is map coloring. In map coloring problems, you need to color regions of a map in such a way that adjacent regions have different colors. Solution technique for CSPs. First, backtracking. Backtracking is a common technique for solving CSPs. It involves selecting a variable, assigning a value from its domain and recursively exploring the search space. If a constant is volatile, if a constant is violated, it backtracks to the previous assignments. Next is constant propagation. Constant propagation involves using the constants to eliminate values from the domains of variables. This reduces the search space and can lead to more efficient solutions. Next, arc consistency. Arc consistency algorithm check the consistency of values between two variables considered by an arc. If values cannot be assigned consistently, they are removed from the domain. Next is heuristic. Heuristics such as the minimum remaining values and the most constant variables MCV help select variables and value strategically to improve search efficiency. Game playing. Game playing in AI involves creating algorithms and game that can play game including board games, card games and video games. The goal is to develop agent capable of making intelligent move to win or achieve a specific objective within the game. So, here are the key concepts. First, game tree. In game playing, a game is often represented as a tree structure called a game tree. Each role represents a game state and the edges represent possible moves or actions. Min-max algorithm. The min-max algorithm is a popular approach for making decisions in two-player games. It aims to minimize the maximum possible loss. In essence, it assumes that the opponent makes the best possible moves and the agent select moves that minimize potential losses. Next, alpha beta pruning. Alpha beta pruning is a technique used to reduce the number of nodes explored in a game tree, making the search more efficient. It eliminates branches that cannot affect the final decisions. Examples of game playing in AI. First, chess. Chess is a classical example of two-player deterministic perfect information game that has been a focal point for AI research for decades. Powerful chess playing engines like IBM's Deep Blue and more recent natural network based engines have been developed. Now come to the week 5, advanced search techniques and knowledge representation. Certainly, let's discuss advanced search technique and knowledge representation. In the context of artificial intelligence, advanced search techniques go beyond basic uninformed and informed search algorithms and are designed to tackle more complex problems efficiently. These techniques are crucial for solving problems with larger and more integrated search spaces. Here are some advanced search techniques. Branch and bound. Branch and bound is an optimization technique used to solve optimization problems. It systematically defined generic algorithms are inspired by some of the process of natural selection. They involving population of potential solution over generations using mechanisms like mutation, crossover and selections. Application. Generic algorithms are used in optimization problem, machine learning and parameter techniques. Next is simulated annealing. Simulated annealing is a probabilistic optimization technique inspired by an annealing process in metallurgy. It also allows algorithm to escape local optima by accepting worst solution with a decreasing probability. Application. It is used in optimizing problems including the traversing salesman problem and job scheduling. Next is practical swarm optimization. PSO is a population based optimization technique where particles move through a search space to find the best solution. Particles are influenced by their own experience and the experience of their peers. In week 5, we explored our understanding of search technique by exploring advanced method like branch and bound. We then delved into knowledge representation, a crucial aspect of AI, and discussed how AI system represent and store knowledge. We also introduced the idea of a knowledge agent, which is an AI system capable of reasoning about and utilizing knowledge. Week 6, logic and reasoning. Week 6 focused on logical foundations of AI. We explored predicate logic, which is used to represent relationships and facts in AI. We learned about well-formed formulas and various inference rules and theorem proving techniques. We discussed two important reasoning methods, forward chaining and backward chaining, which are used in rule-based systems for making decisions. Week 7, knowledge representation models. In week 7, we continued our exploration of knowledge representation by studying different models such as semantic nets, frames and conceptual dependency. We discussed how these models use slots, inheritance, exceptions and defaults to organize and represent knowledge. Week 8, handling uncertainty and learning. Week 8 has dedicated to handling uncertainty in AI systems. We explored the sources of uncertainty that AI systems encounter. We introduced probabilistic inference and discussed Bayes' theorem, which is a powerful tool for updating problems based on new information. Week 9, learning and planning. In week 9, we shifted our focus to learning in AI. We discussed how AI system can adapt and improve their performance over time. We introduced goal state planning, a method for planning and achieving complex goals. We also explored the block word problem, a classical example of AI planning and problem solving. In week 10, the machine learning and natural language processing. In week 10, we delve into exciting field of machine learning within AI. We discussed various types of AI including supervised, unsupervised and reinforcement learning. We introduced the concept of natural language processing and its importance in enabling AI system to understand and generate human intelligence. Week 11, language processing and expert system. In week 11, we explored language processing further by discussing parsing and machine translation, two key components of NLP. We shifted our focus to expert system, discussing why they are essential, their cognitive problem solving capabilities and real world case studies showcasing their applications. Week 12, introducing to Prolog, programming and course wrap up. In this final week, week 12, we introduced Prolog programming, a language commonly used for symbolic reasoning in AI. We covered essential concepts like facts, rules, clauses and lists in Prolog as well as logical operators. Finally, we wrapped up the course summarizing the key takeaways and emphasizing the importance of AI in today's world. This summary provides a detailed overview of course content, allowing students to grasp the key concept and their significance in the field of artificial intelligence. Thank you for watching and we will see you in our next course. Thank you.